In this lesson, we'll look at something called the second fundamental theorem of calculus. And some books don't call it the second fundamental theorem, and they call it the fundamental theorem. It's just, it's related to the fundamental theorem, and let's start by reviewing the fundamental theorem. So if we have this definite integral, we antidifferentiate and then evaluate from 2 to 4. So we have 4 squared and then 2 squared. And we end up with 6. 8 minus 2 is 6. We can do the same procedure, but now we have variables for the limits. So we'll have antiderivative b squared over 2 minus a squared over 2. And we could have function notation and just say, well, here's f prime, so the antiderivative of f prime is f. And then we'll evaluate it a and b. F of b minus f of a. So all of this is what we'll call the fundamental theorem, and then what's next is the second fundamental theorem. So that would be if we have something like that. And it's going to change a little bit. If this is f of t, the value of this would actually be 0, and we would want to have something with a t here and or here. So these would have to be variables with t. But the main concept is, let's take the derivative of the antiderivative, and what's going to happen is it just they just kind of cancel, and we'll see how this all works. But that's what we're going to focus on today. Here's the fundamental theorem, and then if we do the derivative of the integral, now we're looking at the second fundamental theorem. So let's develop this and define what's happening here. So I said that this, because these are constants, this will be 0. Let's see how that works here. And then the rest of the problems will have variables as the limits. So if we did the antiderivative, and we evaluate it from 1 to 2, still taking the derivative, derivative of 2 squared over 2 minus 1 squared over 2, the derivative of 2 minus a half. It doesn't matter what this is, it's 3 halves, but the derivative of a constant is 0. So if we have constant limits and we're taking the derivative, there's nothing special that's going to happen. We already know that's going to be 0. But we're going to look at it when we don't have constant limits. We're going to have a function of t here and or here. And that looks like this. Guess I'll go back and change what I said. I said we need to have a function of t. It's going to be a function of x here. We have a long way of doing it, a middle length way, and a short way. So the long way is, let's actually find the antiderivative. So the antiderivative of t squared over 2, and then we evaluate it from 1 to x, and taking the derivative. We will substitute x squared over 2 minus 1 squared over 2, and then find the derivative of that. Well, the derivative of this is 0, and the derivative of this is 2x over 2, and we just get x. So that's the long way. And a little different notation. Maybe you'll say this is not actually shorter than this, but we're going to ignore whatever function this is and just call it f. So we have the derivative of the integral from 1 to x, f of t dt. It doesn't matter what this is. Whatever's there with a t, just call it f of t. Then and we'll say that lowercase f is the derivative of uppercase f. So instead of doing an antiderivative, we can just use a symbol to say we've done the antiderivative. And on the AP test, capital F is often used to show an antiderivative. So now we substitute, and we'll have capital F of x minus capital F of 1. And we're doing the derivative, so the derivative of capital F, I'll write capital F prime. Capital F of 1 is a constant, so derivative of that is 0. And then we can just say that capital F prime, by our definition, is lowercase f. And lowercase f was the original f of t. Let's say f of t equals t. So f of x equals x. And we get the same answer. Okay, and then we have a short way of doing it, and that looks like this. So we are going to, in this space, we substitute x for wherever there's a t in here. So in this case there's just t, so we'll just put an x in there. And then here's going to be the derivative of x. So that's 1. This is going to be when we substitute 1 into whatever function this is, put a 1 there. And then we do the derivative of 1, and that's 0. So this is x minus 0. And we just we want to stay away from this, actually showing all the work. Here it was an easy function to antidifferentiate, but they can get pretty complicated. We just want to skip all of that work. Alright, pause the video and try that one using all 3 methods. Alright, the long way. Do the antiderivative, so that's t squared over 2 plus t, evaluated from 2 to x, and do the derivative. And substitute the x, so we have x squared over 2 plus x minus 2 squared over 2 plus 2. And then we're going to take the derivative. Rather than simplifying anything, let's just do the derivative of everything. The derivative of this is 2x over 2 the derivative of this is 1, and all of that's a constant, so that's 0. And the answer is x plus 1. All right, if we do it with a symbol and we just say f of t is equal to t plus 1, and we will have d dx f of t dt. Then antiderivative of lowercase f is uppercase F. Then we have capital F minus capital F of 2. And let's do the derivative of this. So that's going to be f prime, capital F prime, and the derivative of a constant is 0. So all we need is capital F prime, which is lowercase f. And we know that f of x is x plus 1. And we want to make sure we're getting the same answer both ways. And then we go to the shortcut, and it's just going to be substitute x into the function. So that's going to be x plus 1 times the derivative of x. Then substitute the 2 into the function, 2 plus 1 times the derivative of 2. That's all 0, and we just get x plus 1. Okay, and then we could have functions in both limits. So let's do this the long, middle, and short way. The long way, we'll do the antiderivative. So we have t cubed over 3 plus t squared over 2 from x to 2x then we all substitute, so we have 2x cubed over 3, 2x squared over 2, x cubed over 3, x squared over 2, and we have to do the derivative. So let's go ahead and simplify or expand that. So we'll have 8x cubed over 3, 4x squared over 2, x cubed over 3 minus x squared over 2, and find the derivative. So this is going to be multiply the derivative using the power rule, multiply by 3. It'll cancel this 3, and we just get 8x squared. Multiply by 2, and we get 4x. Multiply by 3, and we get x squared. Multiply by 2, and we get x. And then we can combine, and we have 7x squared plus 3x. Here we're going to have d dx of integral from x to 2x of f of t, and f of t is this, t squared plus t. Antiderivative of lowercase f is capital F. Substitute, so now we have capital F of 2x minus capital F of x. Then when we do the derivative, we'll have capital F prime of 2x, but That's a composite function. We have the outside and the inside. We need the chain rule, so we're going to multiply by the derivative of 2x. And over here we have f prime of x. We could do the chain rule, but it's just going to be times 1. Now we have lowercase f of 2x, and this will be lowercase f of x. Then we substitute 2x into lowercase f. So we have 2x squared plus 2x minus x squared plus x. We're putting 2x into the t and x into the t, and we have this. So 4x squared plus 2x minus x squared minus x. Multiply everything by 2. 8x squared plus 4x minus 2x squared minus 2x. And combine. Okay, caught a mistake here. 2 is only on this, so here we have 2 on that. 2 on that. I guess we just get rid of that. And now we don't have these 2's here. And 8 minus 1 is 7. 4 minus 1 is 3. And we have to get the same answer both ways. With the short way, we're going to have this, and that means just substitute a 2x into this. So substitute 2x into t, 2x squared minus 2x. Then we have to do times the derivative of 2x. And over here we're going to substitute an x in for t. I wrote a minus, that should be a plus. And now the derivative of x is 1. So we distribute, we have 4x. Nope, don't distribute yet. 4x squared plus 2x times 2. And over here is minus x squared minus x. Distribute 8x squared plus 4x minus x squared minus x. And we'll have 7x squared plus 3x. Alright, pause the video and try that, and let's go ahead and just do this the middle and the short way. Just because we don't want to have to ever do the long way, let's just always focus on, really we're just going to focus on the short way, but let's practice this one too because it uses notation that you need to be used to. Alright, pause the video and try that. So lowercase f is t minus 2. And then substitute the limits. This is using the first fundamental theorem. Now we're going to do the derivative. So we do the derivative of the outside, leaving the inside the same, times the derivative of the inside. That's the chain rule. And you don't have to write the 1. This is now lowercase f. And then we substitute it in for t. So we're going to have x plus 2 for t, and then minus 2. X plus 2 minus 2, and then x plus 1 minus 2, x minus x plus 1, and the answer is 1. Alright, substitute the limit for t, x plus 2 minus 2, and then times the derivative of the limit, that's just going to be 1, and substitute the other limit, x plus 1 minus 2, times the derivative of the limit is 1, and that's x, and then we have minus x minus 1, x minus x plus 1, and we get 1. And we'll stop there.